In this video, we're going to talk about one of your favorite topics ever. That's right, grammar. If we're going to talk about a formal language, that is a mathematical representation of the inputs to our computing system. We can also talk in a formal way about the structure of that language. This is called a grammar. In a grammar, we have things called productions. These are how you produce one well-formed formula, say, from another. So we say that A produces B, and these are strings over the alphabet. And we have terminals and non-terminals. Terminals are where we end things, non-terminals are where we don't end things. We don't need to really get into it this mathematically, but this is going to be the notation that we use when we discuss grammars. So for example, if I start with this symbol S here, this non-terminal, I can then generate an A, which is a letter from my alphabet, and then S and a B, which are two more non-terminals. And then every time you have a S or a B here in this particular grammar, you can keep going. In this way, you can build up larger, what are called sentences. And this is a lot of what we think of grammar in our normal English language as well. We don't have rules of this type necessarily for English. In fact, English is too complex to be captured by rules of this type. But this is a first pass at trying to do so. And if you want to create a computer program that can generate English words, that can generate poems, or can generate narratives, then this is kind of where you start. There's a whole field called computational linguistics, which sort of melds this idea of coming up with a computational way to discuss language that people actually care about, not these formal languages that the computers care about, but human languages. Can we capture enough of the essence of a language like English using symbols such as this, using a grammar such as this, so that we can write a program that can computationally generate things like stories? That's really cool. That's a really interesting area. It touches on who we are as people, it touches on what is language, it touches on what is our mind, and it is computer science as well. So these sorts of things are deep embedded in our field. This is why I keep talking about how the more you know about math, the more you know about other things, the more intellectually developed you are, the more you will see what computer science can do. Maybe you have it in your mind that you want to be a Cerner engineer, or you want to be a web developer, and you only want to take courses that are geared towards those things. I mean, that's great, and go do that and take those courses and develop those technical skills, but not every course is aligned towards those ends. Some of them are here to give you more breadth, and if you take advantage of those while you are able to, because once you leave this university setting, it's going to be a lot harder to access these sorts of ideas. If you take advantage of it while you can, then you will reap the rewards. The rewards that you will gain from this course 5 to 10 years from now are entirely dependent upon how seriously you take it right now. So in any case, as far as we care about this stuff, these are going to be the rules of building up sentences in our languages. So the idea is that if I ever have one of these symbols, S or B, I can replace it with these things. This lambda just means nothing. This basically means I can just drop the S. So if I have an A, S, B, I can replace the S with the lambda, which means it goes away, and I basically just have an A, B. We've got this shorter form here. We can use the bar to indicate or, as we're used to this symbol in our programming languages. So instead of writing S does two things, I can write S does this one or this one. Here are some math things down here. We're not going to be proving theorems about grammars, so we're not going to need to get into this in too much detail, but it's worth reading over, and it's worth understanding all of this. A grammar is a way to discuss the structure of a formal language. And our computational process, we're talking about models of computation. We're talking about trying to capture the idea of what computation can accomplish. It's based on these grammars and these languages, because we can think of everything we're doing in terms of a language built off a grammar. And if we can isolate that, if we can identify what the grammar is for a language that we care about, then we can write programs that interact with that language and can produce strings, can produce sentences in that language. So here's an example here. Can we find the language that this grammar produces? So the language would be all of the possible sentences that you can get out of that grammar, all of the strings that you can get from the start symbol. So my start symbol S and B here, So if I get S, I go to ASB, or this is the same one we talked about last time. So you just look at this and you start to just come up with a pattern. So you see you can start with just nothing, or you can go to ASB, which can give you AB, right? If S then is replaced by the lambda, which can just be AB, if the B is replaced by the little b. So I can have lambda, I can have AB, I can have ABB, B, right? I can have a different set of production rules, right? I can use these rules in a different combination and get an A followed by 3 Bs, or I can get 2 A's and 2 Bs, or I can get 2 A's and 4 Bs. So what you do is you just see what types of strings can I generate from applications of this rule. And then you use your pattern matching skills to say, okay, well, I think what I'm seeing are things of this form, A to the n, B to the n plus k. So I always have some number of A's, that would be n. And then however many number of A's I have to have the same number of B's, plus I can have a few more. So you can never come up with a generation of strings using this grammar where you have, say, fewer B's than A's. That's just not how this works. So you can then take this and you come up with a pattern and you can say this is the grammar. This isn't a mathematical proof, right? To prove this, you'd have to maybe use induction, you'd have to use all these different things, but we're not asking for a proof here. We're just saying, hey, can we look at this? Can we use our pattern matching skills? And can we try to draw some conclusion? Can we describe in a way outside of this grammar what the language is here that we're talking about? And to work through things like this just helps you understand this idea of grammars in the first place. Here's another one. The start symbol gives us A, or it gives us B, C, and then the start symbol all again. So if we can think about this, what we get is we can just have an A that's going to end it, right? Because there's no other S here. So as soon as we get the A, it's over, right? We can't continue the string. But if we get a BC, then we can have an S again. So then we can have as many BCs as we want. So if we look at this grammar, what we can see is that we can have BCA. We has to end in A. There's no lambda here. We don't get to do lambda. So we can do BC, 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 any number of BCs, and then it ends in an A. So here it is, any number of BCs, BC to the n, and then ends in an A. So from this grammar, you can see that this is the language that's generated. Find a grammar for this language. Now we can go the other way, right? You're given a language, let's come up with a grammar, A to the n, B. So I want as many A's as I can get, and I always want to end with a B. So we're going to derive any string of A's followed by B. The production S to AS can be used to derive a string of A's. So this is a useful thing to know. If I want to get any number of A's I want, understand that this grammar rule is going to provide that for you. S to B will stop it and produce the string ending with B. So here it is. It's important to be able to go both directions. Look at some grammar rules and come up with the language. And given a language, can we identify a grammar that can describe it? This is just what we do in computer science, right? We pattern match, we look at structure of things. And that's exactly what's going on here, except the structure that we're looking at is a language. And in a lot of ways, these languages will be our programming languages. Most programming languages out there have, in the depths of them, grammars that you can use to build. There's a grammar out there that'll describe the C programming language. And this is what compilers can use to interpret inputs in that language. So if you're writing a compiler and you want to input a statement in C and unpack it and decide if it's syntactically correct or not, you're going to be programming in some concept of a grammar. And then you can realize what the components are of that line and then convert that into assembly instructions. Or any of our major programming languages. They all have these sorts of grammars that could support them. We've been talking about regular languages. So regular languages have special kinds of grammars called regular grammars. The grammars we've been talking about previously, they have no restrictions at all. But a regular grammar has a restriction. It has to be of this form. So you can't just have any sort of production rules that you want if you want to model a regular language. A regular grammar must be of a particular form. This is what we expect, right? We know how math works. We know that we have different objects that we're studying, and those objects take different forms. So we would expect something called a regular grammar would have a particular form, and this is exactly what's happening. So we have this language, A star, B star, any number of A's followed by any number of B's. So here is the language for that. the grammar for that. AS, remember? AS gives us any number of A's. And the lambda here means that I don't have to have any, and it also allows us to end without any B's as well. So this lambda here does double work. This lambda allows us to start off with, allows us basically to say I don't need any B's anymore, because I can just do A and then S goes straight to lambda. And then B is just going to be, T is going to be replaced by B all the time. So any number of B's. If you don't want any B's, then you just do this one that says AS, and then you replace this S with a lambda. And if you don't want any A's or B's, then you can just start off with the lambda. If you don't want any A's, but you do want B's, then you go straight S to T, and then T gives you all your B's. So you should be able to see here any string that you want, which would be AA, say, or BB, or AABB, right? You can get all of those strings, which are all part of this language, from this grammar. And because this is a regular language, this is a regular grammar. We can come up with these rules. You might be able to come up with other production rules that don't satisfy these conditions that also model this, but that would not be a regular grammar. Here's another set here. This is, we want to start with an A, we want to end with a B, and we want to have any number of C's in between. So the regular expression is A, C star B. These regular expressions are really going to be helpful to us when coming up with our grammars. We can go from a regular expression to a grammar and vice versa. It's going to be a really helpful thing to do. A regular grammar is going to be written this way. S gives you AT, and then T goes to B, or the CT. So we have to start off with the A, and then we go to this T, which is going to be any number of C's that we want. So we can keep replacing T with CT over and over and over and over again, or we can just go straight to B. So you don't have to include any C's if you don't want to, or you can include any number of C's that you want to. And you're always going to end with the B. The terminal here is the B. If we have an NFA, we know that we can have a regular expression for it. So if we have a regular expression, we can have a regular grammar. So we want to now talk about how to take an NFA and get a regular grammar. And we can, this exercise, again, like I said before, this exercise is not about learning a process like integration by parts that is actually useful in science. This process is helping you more deeply understand what a state machine is and what a grammar is. Spending time with these concepts, running through these types of problems will help you be able to see farther in this business. So this is going to show you how an NFA is basically a visual representation, not only just of the language itself, but of the grammar. And these grammars are incredibly important. We can do a lot of work with grammars, as we'll see in the next video, that is difficult to do with the language itself. So state names become the non-terminals. So basically, you just take your state names, and these are going to become the beginnings of your production rules. And then the start state is the start symbol of the grammar, so we'll just replace the state 0 is usually what we've called it. We'll just call it S. And then the state transitions just give us the productions. So if I'm in S, right, I'm going to be able to produce F, or I'm going to be able to produce AI, and that's what you see over here. I'm in S, what can I do? I can produce either just F, right, this lambda doesn't need to be written here, lambda F, the lambda just drops out. So this is lambda edge, that means I'm in S and F at the same time, so that means I can have S go straight to F, so S can be F, or S can consume an input signal and go to I, so AI. Usually we're thinking about this in reverse, right? This is telling us the structure of the sentences in our grammar. And this is a machine that will recognize sentences in the grammar. That's why this is important, to be able to go back and forth. Because we've been building these from objects of this type, but now we're seeing how we can go backwards. This really helps us in our mind get a sense for what's going on with these concepts. And if we want to apply them then in our computer science work, we absolutely can, because these are absolutely applicable things. If you want to interact with text in some way, if you want to interact with a language inside your program, coming up with the grammar of that language and programming it in and allowing yourself to interact with it or generate sentences in it is something that people do. I now, let's look at I. A goes right back to I, and B goes up to F. F, what does F do? F doesn't go anywhere, so F just is a terminal, so it just goes to lambda, and that means you're done. Whenever you get to F, then that means you're done. You're at the end of your string. We can simplify the grammar now to S goes to AI. F, since F just goes to lambda, there's no choices. We can just replace the F with the lambda in both of these cases. So we don't even need the F as a symbol in our grammar. We can simplify it down here. This is really important. You can go from a regular expression to a regular grammar. So first of all, we can draw this NFA to represent this. So remember how we do that. We have any number of A's here in the start state. Then we go to B, A, and then we can do as many BAs as we want here. So if I don't want any BAs, then that means I just stop here, and this is why this is a final state. If I want at least one BA, then I come here, and then I have any number of BAs that I want. So you should convince yourself that this is a legitimate NFA for this regular expression. And then we get a grammar from the machine diagram. So we start with S, go AS or BI, and then from I we go AF, from F we go BJ, or we go lambda if it's going to be a say an A, and then from J we go back to F. So this ends up being the grammar, and you can get that from this, because the final states, remember, have to be able to go to lambda. All the final states have to be able to end. So you come in here and you see that the reason that there's a lambda here on the S and there's a reason there's a lambda on the F is because these are final states. And the whole point of a final state is you have to be able to end there. So if you're building up the grammar and you're in one of the final states, you have to be able to have that input symbol be the final input symbol in your string. You can simplify the grammar simply by doing some basic substitutions here. You can, since I goes only to one thing, basically the way you do the simplified grammar is you look for any production rules that only have a single production, right? If they don't have any ors here, then that means I always produces AF. So you can just replace the I here with the AF. J always produces AF, so just replace the J with the AF. And now you have this simplified grammar. Sometimes in DFAs, we'll have this error state. Remember, we talked about how the NFAs don't have to include this because the NFAs don't have to account for every single possible transition away from a state. But a DFA does. That's the difference between an NFA and a DFA. Even though they are the same power, which we discussed in the last video, the NFA sometimes are easier for us as humans to put together. So this DFA now has to have this state, but it doesn't really matter. It still is the same thing. We just have this state E down here now. All of these transitions are represented everywhere here. Every state now is going to have two transitions for it, and that is because in a DFA we have to account for both outputs. And I say both. Every single thing we've looked at has only had two elements in it, A and B. Partially, that is to make the examples tractable, right? If we had 18 examples, 18 letters, then it would be messy. It would be impossible to work the problems. But it also turns out that if instead of A and B, you called these 1 and 0, we could convert anything that had any number of symbols into one that only had the two symbols. We can basically come up with a binary representation for a more complex language and come up with another language and another grammar that could model it. So in practice, you can actually model anything with something that has these two in it. So, but anyway, this will simplify down to here now because E doesn't go to anything terminal. You can just replace in this way. And we end up with a more simple grammar here as well, because E isn't something that we have to care about, because E is the error state. So E isn't a real state. So what we end up doing is we just drop the E away. It's not deriving a terminal string, which means that the E doesn't help us get anywhere. The whole point of this E state was that it trapped once we broke away from the string. That's why we fashioned this entire business in terms of the NFAs in the first place, because the NFAs don't represent this state. But if you do have this terminal state here that that is just to trap sequences that don't fit the normal progression, then when you see it in your grammar, you just take it away in the simplified form, because doing this over and over again doesn't help. In fact, you can see that if you ever get to E, you're not going to end. You can't use E in a production rule to finish something. It's going to AE all over it. You can't ever end. So this isn't really a legitimate regular grammar. So we have to be able to just cut it out. You can see that it doesn't satisfy this form. W is a non-terminal, is a terminal, but it has to be a B here. If we're going to have a terminal and then a non-terminal, the non-terminal has to be something different than what A was. And that's not what we're seeing here. E goes to AE or to BE. That doesn't satisfy our conditions for a regular grammar. So we just drop them out because it means that we failed to recognize that portion of our string. We can continue the simplification because we've got this J goes to AF, so we can replace the J with AF. All right, we can do anything to anything, right? So here's a regular grammar now, can go straight to the NFA. And just follow these rules. All your transitions, all your transition rules, all of your productions in your grammar just become transitions in your state machine. So we've got this regular grammar here. We can convert this into AI and I to BS. So the first thing you have to do is, this one won't convert straight to a regular grammar, straight to an NFA, because we're talking about two different transitions in the same production. And in a state machine, that's not really how we look at it. So the first step you have to do is put things in the form where it looks just like what you got when you went from an NFA back to the grammar. You have to put everything in the correct form so that it looks more like this. And that's just what this first step is. We introduce new states here in between so that I can go AI and then I gives me BS. So basically this is the simplified version that we've been coming up with. We get back into this form, right? This is more of a normal form, right? More of a canonical form, different forms for different things when we study objects in mathematics, just like we dealt with the conjunctive and disjunctive normal forms in the logic calculus. We're now wanting to put our grammars in different forms for different purposes. This grammar is a wonderful form for some purposes. If we want to write this up in a programming language to interpret some text, this would be a fantastic way to use it. But if we want to come up with an NFA that can recognize this language, then we need to pull back a little bit, and this is not the best form to use. And then this becomes our language. This becomes our NFA, and we can even come up with a regular expression for it. We're always going to come up with regular expressions. We're not getting away from regular expressions. So, big takeaway from this video is dealing with these regular grammars. Understanding what grammars are all about, understanding how they showcase the structure of a language, and being able to do conversions from anything to anything. Given an NFA, give me a regular expression, give me a regular grammar. Given a regular grammar, give the regular expression, get the NFA. You should be able to work with all of these equally well and go from any one to any of the others, because they're all touching on the same idea. They're all touching on the very core of what language is all about.